Second order effects. Our analysis of the MOS structure has thus far entailed various simplifying assumptions, some of which are not valid in many analog circuits. In this session, we described three second order effects that are essential in our subsequent circuit analysis. Other phenomena that appear in submicron devices are studied in chapter. Body effect. In the analysis of figure, we tactically assume that the bulk and the source of the transistors were tied to ground. What happens if the bulk voltage of an FET drops below the source voltage? Since the S and D junctions remain reverse bias, as if we summarize that the device continues to operate properly, but certain characteristics may change. To understand the effect, suppose VS equals to VD equal to 0 and VG is somewhat less than VTH, so that a depletion region is formed under the gate, but no inversion layer exists. As VB becomes more negative, more holes are attracted to the substrate connection, leaving a larger negative charge behind. That is as depicted in figure. The depletion region becomes wider. Now recall the equation that the threshold voltage is a function of the total charge in the depletion region, because the gate charge must mirror QD before an inversion layer is. Figure NMOS device with negative bulk voltage. Here you can see the figure, variation of depletion region charge with bulk voltage. Formed thus as VB drops and QD increases, VTH also increases. This is called the body effect or the backgate effect. It can be proved that with body effect, VTH equal to VTH naught plus gamma root over mod 2 phi f plus VSB minus root over mod 2 phi f, where VTH naught is given by equation phi gamma is equals to root over 2q epsilon Si n sub by C naught x denotes the body effect coefficient, and VSB is the source bulk potential difference. The value of gamma typically lies in the range of 0.3 to 0.4 volt 1 by 2. For body effect to manifest itself, the bulk potential V sub need not change. If the source voltage varies with respect to V sub, some phenomenon occurs. For example, consider the circuit in figure A. First, ignoring body effect, we note that as V in varies, V out closely follows the input, because the drain current remains equal to I1. In fact, we can write I1 is equals to 1 by 2 nu n C naught x W by L V in minus V out minus V TH whole square, including that V in minus V out is constant if I1 is constant. Figure B. Figure A. Circuit in which the source bulk voltage varies with input level. B. Input and output voltages with no body effect. C. input and output voltages with body effect. Now suppose the substrate is tied to ground and body effect is significant there as V in and hence V out become more positive. The potential difference between the source and the bulk increases, rising the value of VTH. Equation therefore implies that V in minus V out must increase so as to maintain ID constant. Figure C. Body effect is usually undesirable change in the threshold voltage, that is, as in figure A, often implicates the design of analog and even digital circuits. Device technologies balance N sub and C naught X to obtain a reasonable value of gamma. Channel length modulation. In the analysis of channel pinch-off in session, we noted that the actual length of the inverted channel gradually decreases as the potential difference between the gate and the drain increases. In other words, in equation L naught is in fact a function of VDS. This effect is called channel length modulation. Writing L dash is equal to L minus lambda L, that is L by L dash similar to 1 plus delta L by L, and assuming the first order relationship between delta L by L and VDS such as delta L by L equal to lambda VDS, we have in saturation ID is similar to 1 by 2 nu n C naught x W by L VGS minus VTH whole square into 1 plus lambda VDS. Here you can see the figure. Finite saturation region slope resulting from channel length modulation, where lambda is the channel length modulation coefficient illustrated in figure. This phenomenon results in non-zero slope in the ID VDS characteristic and hence a non-ideal current source between D and S in saturation. The parameter lambda represents the relative variation in length for a given increment in VDS. For large channels, lambda is smaller. With channel length modulation, some of the expressions derived for GM must be modified. Equations are respectively written as GM is equal to nu n C naught x W by L VGS minus VTH into 1 plus lambda VDS is equal to root over 2 nu n C naught x W by L ID by 1 plus lambda VDS, while equation remains unchanged. The linear approximation lambda L by lambda directly proportional to VDS becomes less accurate in short channel transistors, resulting in a variable slope in the saturation ID VDS characteristics. We return to this issue in chapter 16. The dependence of ID upon VDS in saturation may suggest that the bias current of a MOSFET can be identified by the proper choice of the drain source voltage, allowing freedom in the choice of VGS minus VTH. However, since the dependence on VDS is much weaker, the drain source voltage is not used to set the current. The effect of VDS on ID is usually considered an error, and it is studied in chapter. Subthreshold conduction. In our analysis of MOSFET, we have assumed that the device turns off abruptly as VGS drops below VTH. In reality, for VGS similar to VTH, a V inversion layer still exists and some current flows from D to S. Even for VGS less than VTH, ID is infinite. ID is finite, but it exhibits an exponential dependence on VGS called subthreshold conduction. This effect can be formulated for VDS greater than thoroughly 200 millivolts as ID is equal to I naught expression VGS by nu VT, where nu is greater than 1 is non-linearity factor and Vt is equal to Kt by Q. He also said the device operates in weak inversion except for nu. Equation is similar to the exponential IC by VB relationship in bipolar transistor. The key point here is that the VGS falls below VTH, the drain current drops a finite rate. With typical values of nu at room temperature, VGS must decrease by approximately 80 millivolts for ID to decrease by 1 decade. Figure, for example, if a threshold of 0.3 volts is chosen in a process to allow low voltage operation, then VGS is reduced to 0. The drain current decreases only by a factor of 10 power 3.75 exponential, especially problematic in large circuits such as memory. Subthreshold condition can result in significant power dissipation or loss of analog information. It is appropriate at this point to return to the definition of the threshold voltage. One definition is to plot the inverse on resistor of the device. R on minus 1 equal to mu C naught x W by L VGS minus VTH as a function of VGS, and extrapolate the result to 0, for which VGS is equal to VTH. In rough calculation, we often view VTH as the gate source voltage, yielding ID by W is equal to 1 mu m in saturation. For example, in a device with W equal to 100 mu m operates with ID equal to 100 mu a, it is in the vicinity of the threshold region. This view is nonetheless vague, especially as the device length scales down in every technology generation. We now re-examine equation for the transconductance of MOS device operating in the sub-threshold region. Is it possible to achieve an arbitrary high transconductance by increasing W while maintaining ID constant? It is possible to obtain a higher transconductance than that of a bipolar transistor. RC by VT biased at the same current. Equation has derived from the square law characteristic ID equal to 1 by 2 nu C naught x W by L VGS minus VTH square whole square. However, if W increases while ID remains constant, then VGS it tends to VTH and the device enters the subthreshold region. As a result, the transconductance is calculated from equation to be Gm equal to ID by nu Vt, revealing that MOSFETs are inferior to bipolar transistors in this respect. Thus, the exponential dependence of ID upon VGS is in subthreshold operation may suggest the use of MOS device in this regime so as to achieve a higher gain. However, since such conditions are met by only a large device with or low drain current, the speed of subthreshold currents is severely limited. Voltage limitations. MOSFETs experience various breakdown effects if their terminal voltage differences exceed certain limits. At high gate source voltages, the oxide breaks down irreversibly damaging the transistor. In short channel devices, an excessively large drain source voltage widens the depletion region and the drain so much that it touches the at around the source, creating a very large drain current. This effect is called punch through. Other limitations related to hot electron effects are described in chapter. Thank you.